Hello, Mr. Price here, and this is the fifth video of the January 2007 Mechanics 2 paper. This one is another work, energy and power question. Let's have a look. So we've got a three-parter here. We have a train of mass 100 kilograms. It's moving at a speed v, and resistance to motion is 3v squared, and the power output of the train is 3000 over v. Okay, and we're being asked to find the driving force acting on the train. So we're being told the driving force on the train is 120 newtons at a particular instant when it's moving at 5 meters per second. Okay, so we're showing this. So, slightly unusual work energy power question. I suppose this one's a little bit unique, but we just do our usual things and it should all work out well in the end. So, here's my train. Okay, and it has a driving force F. It is travelling at a particular speed, and its resistance to motion is 3v squared. Okay, so we know that the power is 3000 over v. Watts, and it is 100 kilograms. So we know that the power is also equal to a force times the velocity. So let's substitute some values in here. So at a speed of 5 meters per second, substituting this into here, the resistance to motion will be 75 newtons. We want to know this driving force. And we know that the power is 3000 over v, so 3000 divided by 5 gives us 600 equals Fv, so that gives us a force of 120 newtons. Okay, a little bit unusual, let's think about that there for a slight second, but just use one of the values we're given and we can show that for that particular speed, that is our force. Okay, now let's look at part 2. We want to find the acceleration of the train at the instant when it's moving horizontally with a speed of 5 meters per second. So the situation we just had pretty much. So this is where this diagram is going to come in handy. So we know this is 120. So this is an unbalanced force. So the overall resultant force, F resultant, is 120 minus 75. Okay, and this is equal to MA, where we know the mass is 100 kilograms. So solving this, we should get an acceleration of 0.45 meters per second squared. And that's all we need to do for part 2. Nothing too strenuous there. Okay. Part 3, this one's a little bit more trickier, and we'll probably need a force diagram for this one. So now, excuse me, the train is moving with a constant speed up a straight hill, inclined at an angle to the horizontal. and we're told what this angle is, and we want to calculate the speed of the train. And all those previous information were given to us still kind of applies. So let's just quickly model this. So here's alpha, and I'm told that sine alpha is equal to 1 over 98. Okay, so there's my train. There's a force here, a resistance here. There will be a reaction force, but we don't really care too much about that. And then mg here at an angle of alpha. Okay, so we'll just write down everything we know again. So P equals Fv, and we also know, doing some rearranging then, that P over V equals F. And we also knew earlier that the power is 3000 over V, so substituting that into there, we get 3000 over V squared is the force. Okay, now what are we told here? It's moving at a constant speed. Okay, constant speed. So our system is in equilibrium. So we can say that the force 3000 over V squared is equal to the resistance, which is 3V squared, plus mg sine alpha, which we know is 1 over 98. It's a bit blurry, so let's see if I can fix that. Okay. So, doing some rearranging here, we get 3000 equals 3v to the power 4 plus mg 1 over 98 is 10, so 10v squared. So we can say that 3v to the power 4 plus 10v squared minus 3000 equals 0. Okay, so here we've got a hidden quadratic. So if we let a equal v squared, we now have 3a squared plus 10a minus 3000 equals 0. So now if you solve this quadratic, we should get an a value of 30, or a negative value which we can disregard. And now we know that a equals v squared. So v squared equals 30, so v is root 30 meters per second. And that is question 3 done. That was quite a tricky one actually, so really well done if you kind of followed most of that and saw what was happening. The key to this is not not doing exactly what I was doing, but sort of just follow the methods that I took. So write down everything that I know, equate it into one formula as much as possible, and then see what's happening in your force diagram. And once you know that it's constant, you can start to resolve forces to know that these two are going to equate. Okay, and that is question 5 done.